translation tolerance as a test case to compare humans and artificial neural networks in their capacity for generalization. So, online translation tolerance can be defined as the ability to generalize recognition of an object at a trained retinal location to an untrained retinal location at which the object has not been experienced. So, for example, if we wanted to assess this in humans, we could train participants to recognize a novel object like that one at a trained retinal position, and then assess accuracy at a displaced location, at a location at which the object has been displaced by degrees of visual angle. And similarly, you can assess online translation tolerance in artificial neural networks by displacing that novel object by a number of pixels. So, to what extent is online translation tolerance in humans and in artificial neural networks? So, I'll begin with humans. So, this is a plot that summarizes previous psychophysical studies, and on the x-axis we are plotting performance accuracy at the trained position, and then the black dots represent performance accuracy after that object has been displaced by x amount of visual angle. So you can see that in studies labelled 1 to 4, we actually see quite restricted capacity for generalization in these participants, such that after displacing the object by just a few degrees of angle, we see quite a marked decrease in performance. However, as all of these studies use those kind of stimuli, which are 2D, quite unnaturalistic, and quite difficult to differentiate in some cases. And therefore, that might encourage participants to use low-level visual representations that are highly retinotopically constrained, and that might explain this marked fall in performance. Indeed, if you take a study that uses more 3D naturalistic objects like those, more like those objects that are displayed at the bottom there, we see those studies illustrated with numbers 5 and 6, so the dotted lines, and we see more robust demonstrations of translation tolerance. We see flatter lines and up to 8 degrees of visual angle. However, this online translation tolerance is only demonstrated up to 8 degrees of visual angle, and therefore it's still a somewhat limited demonstration of online translation tolerance in human participants. So what we wanted to do was test whether this online translation tolerance could be extended to larger displacements. So to do this, we took these 24 novel objects that look familiar to everyone who's at the talk at 9 a.m. They were taken from the Charles Leak 2016 study, so if Charles is in the audience, thanks for allowing us to use that stimuli. So we took these 24 novel 3D, slightly more naturalistic objects. And what we did was we trained participants to differentiate amongst these objects, so to recognize these objects as either A or B at one trained retinal location using gaze contingent eye tracking. So they're looking at the fixation cross as they see these objects. And then after training, we displaced those objects by up to 18 degrees of visual angle. So we're actually displacing these objects by more than twice the displacement that previous studies have used. And indeed, if we look at the accuracy performance, even after this sort of displacement, performance of participants is showing pretty high accuracy rate of 83% classification after those displacements, and therefore showing some degree of online translation tolerance. In experiment 2, we wanted to see if this could be somewhat boosted. So we did this by using a paradigm called location training. So instead of the objects just all being trained at one location, we split them in half. And we trained half the objects on the right and half on the left. And then at test, we swapped those positions. So you'll see the object that was trained on the right is then tested 18 degrees in a shifted position on the left. And the same with the other case. So what we're doing is we're taking away the unfamiliarity of performing a task at that test location, because they haven't seen that object there before, but they performed a task with another object at training. And again, we see a somewhat boosted performance. So performance goes up to 89% at the 18 degrees displacement. To compare that to what performance is at the training condition, performance is 97% in that case. So overall in those studies with humans, we showed that online translation tolerance in humans was demonstrated at displacements that were more than twice shown by previous studies. So it shows that humans certainly have a quite broad capacity for online translation tolerance. So what if I were to take a state-of-the-art convolutional neural network and do a similar thing with that? Could that capture the human capacity for generalization? So intuitively, the convolutional neural net should be well suited to this, given its primitives of convolutions and pooling. So its architecture should be well suited for this. However, the standard training procedure used in CNNs uses multiple exemplars of the same category, so multiple exemplars, say a dog, trained over a range of retinal locations, because typically they're not really interested in testing online translation tolerance. They're typically just interested in accuracy of categorizing objects. So they'll use an extreme form of data augmentation in a way. Indeed, I'm only aware of 4 studies that have actually investigated CNN's capacity for online translation tolerance, which I summarize here. So just to go back to that, these this appears with that standard training procedure, as a consequence of that, you would only be able to test a highly limited form of online translation tolerance. So I summarize those 4 studies that have looked at online translation tolerance here. So all of these studies took an image set like MNIST or something and trained those objects at one centered location in retinal space. And typically those objects are 28 by 28 pixels. So trained at a single location and then displaced by 10 to 30 pixels. So a displacement that is roughly the same width of the image itself. And you can see in the final column that performance is not particularly impressive. The highest performance in this case is 50% accuracy. So a couple of studies tried to do a bit more with training, such that they used kind of minor data augmentation. So, for example, in the training set, they randomly displaced each image with 4 locations at training and then displaced it. So you see performance improves slightly in the case of Cordra Adams to 50% from 5%, but still that's not particularly impressive. And then in the case of Furukora, performance improves to 80%, but they are only shifting the image by 10 pixels at most, which is about 1/3 the width of the image itself. So all of those studies have a number of common limitations, because firstly, none of these studies actually displaced in terms of comparing it with humans, none of these studies displaced the test images by a width that is more than the image itself. So this is unlike our psychophysical studies, where we were displacing the objects by about at least 2 times, maybe 3 times the width of our own images. In those CNN studies, they're not even displacing it by 1 image width. So they're not testing the same extent of online translation tolerance as in psychophysical studies. And even so, generally, they showed quite highly limited online translation tolerance. Second of all, none of these studies used a mechanism called global average pooling, which has become more common in CNNs recently. And what global average pooling does is it gives you larger receptive fields at higher level units, which intuitively should support translation tolerance. So in this set of studies, we wanted to manipulate three factors with this in mind. We manipulated global average pooling versus no global average pooling. We used some level of data augmentation so that images were displaced no distance or random displacement of objects up to 20 pixels. And we also used single-sided training or two-sided training like experiments 1 and 2. We also used larger displacements, which I'll get on to in a minute. So to do this, we took VGG16 CNN, and we applied all of those manipulations. So this VG16 is pre-trained on ImageNet, and then we trained it on these stimuli here. So the stimuli we used in psychophysical studies, so 30 by 30 pixels in a large retinal space of 400 by 400 pixels to give us more space for training, more space for displacement. And in conditions equivalent to our experiment 1, let's just go through no data augmentation first. With global average pooling and 30 pixel displacement, so similar displacement as the image with, performance was at 96%. And then without global average pooling, similar high performance. But then when we go beyond the width of the image to 110 pixels or more, the performance is only high, 98%, with global average pooling and not without global average pooling. And it's a very similar story when we use data augmentation versus no data augmentation. Also a practically identical story with single-sided versus double-sided training. So to finish up, it has important implications for our understanding of translation tolerance. So our psychophysical studies show online translation tolerance over displacements twice the extent of previous studies. And CNNs can capture this human-like capacity for generalization as long as they have this global average pooling mechanism. If they don't, they struggle to do so. So I think I'm on time, so I'll open up to questions.
Time for one quick question. Go ahead.